is V, then of course T, that is a subgroup, also acts on this vector space. And now comes one of the theorems I consider most important in mathematics. Namely, so by a torus, by the way, I mean an algebraic torus, just to be clear, C star to the n. Now, when a torus acts on a vector space, the vector space decomposes into one-dimensional representations. So if T acts on V, then V equals a sum of V lambda, where lambda are homomorphisms from the torus to C star. So what are the homomorphisms from C star to the n to C star? The only ones are when we take x1 up to the xn and we map them x1 to alpha 1, let's say lambda 1, times xn to lambda n, where lambda I are integers. These are the only group homomorphisms from a torus to C star. So in other words, we think about it as a lattice. Just n tuples of integral points. Of course, one lambda corresponding to Zn can appear a few times. So you can have, for example, a trivial representation of dimension 4, which would mean just 4 copies of V0, just 0, 0, 0. So by V lambda, the action of T on V lambda for small V lambda inside big V lambda is just lambda of T. So remember, lambda is a homomorphism from T to C star times V lambda. And yeah, that's all. So in other words, on each V lambda, the torus acts just by rescaling. It just rescales vector according to, this is called a character. And the lambdas that appear when we have a G are very important, even when we look at G. They are called weights of a representation. Now, it's customary to fix an order. Let's say we fix a lexicographic order on Zn. And now we can ask which weights appear in the decomposition of V, and what's the highest weight. Yeah? So there is a unique highest weight, let's say lambda 0, and then V lambda 0 is just one-dimensional. So in particular, we can talk about highest weight vector, which is determined up to scalar. So this is an element of this one-dimensional. So this is just C. This is just one-dimensional space of complex numbers. And then any vector here, V lambda 0, this is determined up to scalar, is called a highest weight vector. Now, representations can be reducible. I should say fix a lambda. This is true for an irreducible representation. For irreducible representation. In other words, V, if it's a sum of two representations, V1 plus V2, then one of them is trivial. Then V1 is 0 or V2 is 0. That means irreducible. This is a definition of irreducible, that you cannot write V as a sum of two vector spaces on which G acts. Of course, you can always write V as a sum of two vector spaces, but the thing is that you want the action to restrict. And for SLN, the theory is very beautiful. Namely, we have bijections between irreducible representations, highest weights, and Young diagrams with at most n-1 rows. So this is for SLN. Okay, so I told you what's an irreducible representation. I told you what's a highest weight. It's just the highest weight that appears in some representation with respect to a fixed order. I haven't told you what's a Young diagram. So instead of giving a formal definition, let me just present you examples. So Young diagrams are such gadgets that have rows, and in each following row you can have you can have equal rows, but you cannot have more boxes in a row that is lower. You can only have less or the same number of rows. And then this is the number of rows. Okay, so this looks like an abstract theory, so let's make some examples of some irreducible representations. So there are two well-known irreducible representations of SLV. And one is the let's say kth symmetric power, and one is the kth wedge power. So first, what are the weights here? So which vectors, when we act with a diagonal matrix, gets only rescaled by some number? So if we take EI1 ... EIK, if we act with lambda 1, lambda n, 0, 0, this is our torus element, we are getting a product of Tij from j equal 1 to k. Lambda, I call them lambda, lambda ij, and the same vector, ei1 times eik. Yes, is it clear? When I act with this matrix on every single vector, each one gives me one lambda. So altogether, the vector is just rescaled. So these are my weights vectors. And the weight, well, I just have to remember the exponents. So the weights are depend what is the exponent of a given lambda. So what will be the highest weight vector on this example? So I want to have as many lambda 1s as possible. Then among those, I want to have as many lambda 2s as possible. So which weight vector will be the highest weight vector? Any guesses? So how can I have a lot of lambda 1s? Which vectors should I have to get a lambda 1, to have it multiplied by lambda 1? E1, I should take an E1. So if I take an E1 times E1, yeah, if I multiply it by lambda 1, lambda n, I'm just getting lambda 1 to the k times the same vector. Yeah? Now this lambda 1 to the k, this is lambda 1 to the k times lambda 2 to the 0 times lambda n to the 0. So the weight, the exponents, are k, 0, 0. Yes? And that's my highest weight. Highest weight. And the vector E1 times E1, this is the highest weight vector. Yes? And the corresponding Young diagram, So I got from a representation to highest weight. Now I have to produce a Young diagram. Well, the weight just tells me how many boxes I should put in each row. So here the Young diagram just has k boxes in the first row, and no boxes in the second, no boxes in the third, and so on. Yeah? So on this example of Sk, we went through those bijections. One more. Now we go to the exterior power. Wedge KV. Okay, so what will be the weight vectors? Again, this will be wedge products of basis vectors. But now look, yes?
I'm sorry, can you say, why did you start with E, I1, but E, E, IK?
Because only those vectors are changed by a scalar when I act with a diagonal matrix. Because if I would have a sum of such two, everyone would get a different scalar. So the vector as a sum wouldn't be just rescaled. It would be changed to a different vector. And weight vectors are by definition those that are just changed by the scalar. So in other words, I take a torus action on this space, and I look at the representations. So
you want the one-dimensional?
Yes, the one-dimensional on which the torus just rescales.
Those are the only ones.
Those are the only ones. Okay, so which are for the wedge? Again, these are just wedges of a vector basis. Yes? Wedges of vector basis, they are just rescaled, because each basis vector gets rescaled. But now look that I cannot have two E1s, because if I had E1 wedge E1, I would get 0. So what will be now the highest weight vector? Well, I want one E1, because this is as much of them as I can get. Then I want as much E2s as I can get. Then as much E3s, and up to Ek. Yeah? And now when I act with lambda 1 up to lambda n, I get a, I get a lambda 1 times lambda k, E1, wedge, Ek. So here I get 1s, and here I get lambda k plus 1 to 0. Yeah, and so on. So now my weight vector is 1, 1, 1, and then zeros. Ones are k times. Yeah? So the Young diagram now has one box in the first row, one box in the second, and so on. And altogether, this is my Young diagram for the exterior power. Okay. Now, there is a beautiful geometry behind representation theory. Namely, if we have an irreducible representation, then there exists a unique closed orbit in the projectivization. Okay? So the group acts here, and there is a unique closed orbit. You can maybe guess this is the orbit of which vector? The orbit of the highest weight vector. So you can ask, what would happen if I would change the order? Because I chose a lexicographic order. I would get a different highest weight vector. But it would be in the same orbit, in the same G orbit. And these varieties, this is an orbit, so this is called the homogeneous varieties. They are very, very well studied, and they are central in mathematics. So, for example, here, if you start with E1 times E1, when you start acting with a group, with your SLN, you are getting an arbitrary V times V, because you can always find a matrix that sends E1 to a given vector. So you are getting a Veronese in this case. Yes, you see? You are getting all vectors V dot 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 V that I introduced last time. So for this one, this unique closed orbit is the Veronese. And for the wedge power, when we have E1, E2, wedge EK, we can once again send them to any vectors that we want, but to linearly independent vectors. Yeah, these are linearly independent, so my group has to send them to linearly independent. So in other words, I'm getting a V1, wedge, 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 VK, when those are linearly independent. This is the Grassmannian. Yeah? You can identify such a class of such vector with a vector space it spans. So another closed orbit in this other representation is the Grassmannian. And all of them, because they are orbits, they are isomorphic to G mod P, where P is the stabilizer of the highest weight vector. Stabilizer of highest weight vector. This is called the parabolic subgroup of G. So parabolics are those that contain a Borel subgroup. Or in other words, these are the only groups when this is projective. These are such subgroups that the quotient has a structure of a projective variety. Okay, or in other words, these are such subgroups that contain a maximal solvable subgroup. But this will not be very important for the rest of the talk. Now, a beautiful theorem. So we are going towards Professor Kwak's questions, why there were no quadrics in the secant variety. But before we go there, I have to say something about quadrics. Namely, there is a beautiful theorem due to constant that if we look at the ideal of such G mod P, when G is semi-simple, semi-simple means that the radical is trivial, so that there are no normal solvable subgroups. Then the ideal is generated by quadrics.
Do you have some description for P?
Stabilizer of the highest weight vector. So for example, in case of Grassmannian, we take such matrices. So anything here, anything here, anything here, and here 0.
Yeah, the P is still unique because of the unit orbit.
This P, yes. Well, it's unique up to like conjugation for once you fix a representation. Okay. So this is generated by quadrics. Of course, there are no linear equations because it's a non-degenerate variety. Okay. And yeah. Okay. Now a little bit of representation theory. So when V is a representation of G, and if G also acts on X in PV, then everything, the degree D point, the degree D polynomials in the ideal, this is also a representation of G. So because G acts on X, and in the same way, the degree D part algebra. So we can take degree D polynomials and divide them by the degree D part of X. This is also a representation of G. So one can hope that maybe, note that when G acts on X, G also acts on arbitrary secant variety of X. Yeah? Because the secant was a linear condition. So maybe let's try to understand this as a representation. And what do I mean by understanding it as a representation? Well, every representation decomposes into irreducible representations with some multiplicity. So V lambda is irreducible. V lambda to alpha I, this is called an isotypic component. And lambdas are over highest weights. And such a decomposition is unique. So this would be a far-reaching aim to understand the ideal as a representation. Now, there is a problem there in this approach. And the problem is that before you want to understand the variety, you should understand all of the polynomials. You should first understand the projective space. So let's take the one representation that we know, that is the symmetric power. And let's try to understand the degree k polynomials on this vector space. So the degree 1 polynomials, this is just the dual. Yeah? And the degree k polynomials, this is the kth symmetric power of this thing. So these are homogeneous degree k polynomials on SDV. Now, the main problem is that this is open now for 100 years. No one knows how to decompose it as GLV representations. This is called plethism. Only for small k it's known. Okay, but maybe still we can do something. So maybe instead, for example, of either understanding the ideal, maybe we can understand the quotient. And this is in fact how constant theorem is proved. So now each of my lectures has at least one proof. So now there will be a result with a proof. So a proposition. It may seem not related, but it's strongly related. If we have a variety, a projective variety, non-degenerate. By non-degenerate, I mean that there is no linear equation that vanishes on it. Then no polynomials of degree smaller than k vanish on sigma k of x. So this is why there were no quadrics on the second secant variety. Proof. So take maybe before I start,
K or equal, right?
Smaller or equal to k. Yes, sorry. Before I start the proof, one thing of a notation. If I have a polynomial, homogeneous, of degree k, then there is a gadget that goes under the name polarization. Namely, there is a k-linear form, a unique k-linear form, such that if I symmetric k-linear form, I mean symmetric, such that when I evaluate it on the diagonal, I get p of x. So if you want to get this form and evaluate it on other vectors, you just have to differentiate p in directions of these vectors. That's how this p tilde can be defined, and it's quite easy to see that it's unique. It's a very handy tool, as we will see now in the proof. So let's take a polynomial of some degree d in the kth secant variety of x. Well, a polynomial belongs here even only if for any x1 up to xk in x, and for any lambda 1 up to lambda k in C, p of some lambda I xi equals 0. Yeah? Vanishing on a secant variety means vanishing on an open set of the secant variety. This is even only if for any x1 up to xk, for any lambda 1 lambda k, p tilde of sum of lambda I xi, now I have to copy it. I have to copy it d times, equals 0. Yes? I just use this polarization, and I just add a tilde and copy it on the diagonal. But now, this form is symmetric and linear, so I can start expanding it. I just treat it as a product. So this is even only if for every xi, for every lambda I, and now I have a sum of lambda I to alpha, let's say lambda to alpha, p tilde of x to alpha. Now I have to say what do I mean. Here alpha is a partition. This was a degree d polynomial. Yes. So in other words, alpha is a partition alpha 1 up to alpha k, and the sum is equal to d, and lambda to alpha means lambda 1 to alpha 1 times lambda k to alpha k, and p tilde of x to alpha means just p tilde of x1 x1 alpha 1 times, and so on, xk xk alpha k times. Is it clear what happened in this equivalence? I just used the fact that this is a k-linear form. So I can expand this sum outside. I can expand all of the sums outside. So, you know, when you have a product, it's like you have to choose one entry in each sum. So this alpha encodes the choice. How many times I chose lambda 1 x1? Alpha 1 times. How many times I chose lambda 2 x2? Alpha 2 times. And then I go with lambdas before the bracket because the form is linear. And what I'm left with is my choice of x1s, alpha 1 times, and xk's, alpha k times. Okay, but now this is a polynomial in lambdas that vanishes for every lambda. So this is even only if for any x1 up to xk, and for any partition alpha 1 alpha k of d, we have p tilde of x1 alpha 1 times. So I will use this shorter notation. X to alpha equal to 0. Yes? Such a thing can be, I didn't write equal to 0. Such a sum equals 0 for any lambda, even only if all these numbers are equal to 0. Otherwise, if at least one of them is non-zero, then I can find lambdas such that this polynomial is non-zero. Okay, and now I claim that this is enough. I claim that this implies if d is less or equal than k, that p is 0. So let me prove this implication. And this last implication, of course, will finish the proof. So note that when k is greater than d, I can put all the x's here. I can take the partition 1, 1, 1, 1, 1, 1 of d. Yeah? I can take distinct x's. So in particular, I know that for any x1 up to xk in x, any x1 up to xd, px1 xd is equal to 0. Yeah, can you see? I just take the partition when k is big. I can take the partition 1, 1, 1, 0, 0, 0 of d. Yeah, I can take once x1, once x2, and so on. Yeah, this I can do only when k is greater than d. Otherwise, there is no such partition. I need to have some repetitions when d is greater than k. But now, when I evaluate p on any vector, because my variety was non-degenerate, any vector decomposes as a sum of alpha i's and some xi's. Yeah? But now I can write it as p tilde of the sum alpha I xi, sum alpha I xi. And again, I can expand as here, but now, using this, I will get that all of those coefficients are 0. Because no matter which choices I make, yeah, I always get something that I already know that is 0. Yeah? If I take twice x1, then x2, then x3, well, I know whatever x's I take, this is 0. And everything that I will get here in an expansion will be p tilde of some x's. So everything here will be 0. So in particular, I prove that p on any point is 0. So this implies that p is 0. That's why there are no polynomials of small degree in the secant variety. And this is also one of the reasons why it is so hard to find equations of secant varieties, because they tend to go higher and higher. So I planned to make a harder version of this theorem in the language of representation theory. But maybe this is not a good idea, and maybe I will instead pass to something more hands-on, and I will show you how to estimate ranks of tensors on some very down-to-the-earth examples. Okay. So maybe just let me tell you to conclude. This thing adapts to a representation theoretic language. And you can, using this trick of partitions and taking a few times x1, x2, and so on, describe the ideal as a kernel of certain representation theoretic maps. But it's not that easy to control those maps. And this is in particular how Claudio Raicu proved his theorem. He was able to control those maps on small examples. If you want to read more, I will just maybe give you a reference. This is in chapter 5. So don't look at earlier chapters because they are more complicated. But chapter 5 is easy. In 1401, this is an archive reference. This is also published in Linear Algebra and Applications. 1956. So there is an adaptation of this method to a representation theoretic setting.
X does it have to be irreducible, or can you do anything if it's reducible?
I think here I used only the fact that it's non-degenerate.
So that is also true for arbitrary reducibles?
Yes.
Yes.
I mean, I don't see anywhere where, I always work with irreducible varieties, but this particular example, I think it works, this particular proposition, I think it works always. Okay.
But is it possible there is no k plus 2 polynomial as generator?
It happens. So usually it's not a good word because there's no measure on varieties, but on easy examples, degree k plus 1 is enough. Like for example, for sigma 2, degree 3 equations were enough. But there are examples when there are no degree k plus 1 equations. Okay, so let's focus on something easy. Let's take a tensor product of three spaces. 2 would be not enough because then we would be just dealing with matrices with A, B, and C all the same and isomorphic to Cn. Now I will be exchanging open problems and what we know. So there are two amazing open problems. Very important from the point of view of complexity theory. Provide a tensor of border rank greater than 2n. So what do I mean by provide? Write it explicitly with, let's say, small integer coefficients. Now, this is amazing because a generic point, you know how to estimate the dimension of the secant variety, has border rank about this, about n squared. And we cannot even provide tensors of high linear border rank bound. Even maybe more amazing, provide a tensor of rank greater than 3n. These are all open problems, and very important open problems because of computational science. So I will finish with last theorem. Proposition, very easy. So how to estimate a rank of a tensor? If we have a tensor in A, tensor B, tensor C, we can consider all contractions by a linear form in A. So I take an arbitrary linear form on A, and I act with T, and what I obtain is a space of matrices. Space of matrices. An example will be on this board. This is in fact an example just 10 days ago JM sent me and asked for the rank. So I write a tensor. I promised something very much hands-on. There will be nothing more explicit. Yeah, we have a tensor. Now, how would you say what's its rank? Well, it seems that the rank is 6 because it's a sum of 6 simple tensors. Yeah, each one is really a sum of 2 things. Yeah. So the question is the rank 6, or maybe not? Now, what is this space of matrices I'm talking about? Well, there are 3 possible contractions. We can either contract with E1 star, then we kill completely this part, and we are just getting this matrix. So what kind of matrix is this? Well, it's a matrix that has a 1 on entry 1, 2, and a -1 on entry 2, 1, and zeros otherwise. Then there is a E2 contraction, which gives us a 1, -1. And then there is an E3 contraction, which gives us 1, -1. The entries that I'm not writing are zeros. So in other words, the space of matrices is the following three-dimensional space: A minus A, B minus B, C minus C, 0. So this is a space of matrices. And the proposition says that T has rank less or equal to K, even only if there exist B1 up to Bk rank 1 matrices such that A star of T is contained in their span. So in other words, instead of thinking about the tensor, that is quite complicated gadget, you just have to think what's the minimal number of rank 1 matrices that span this subspace. That looks a very hands-on question. So in particular here, if you think about it for a while, you will find 5 matrices, 5 rank 1 matrices that span this subspace. If you don't want to think, I can give them to you. There is 5 of them. So for example, if you want to obtain A minus A, you sum up those two. If you want to obtain C minus C, you sum up those two. Now, how to obtain B minus B? Well, we note that if instead of summing those two, we take a difference of those two, we get a matrix 2 minus 2, 0, 0, 0, 0, 0, 0, 0. And if instead of summing those two, we take a difference of those two, we obtain a matrix 0, 0, 0, 2, 0, minus 2, 0, 0. Now, if we... did I do this correctly? If I subtract... Oh, the last one should be with minuses. Sorry. Now, if I add those two matrices, I obtain a 2, 0, 0, 0, 0, 0, 0, 0, 0, 2. And now you can see, if I add those, there is a minus 2. So I can kill off this 1 and minus 1 from the last matrix, and I get a B. Yeah? So this is an easy proof that at most rank is 5. It's not 6. And to prove that it's indeed 5, it's quite easy because there is an equation for rank 4 tensors, and you just evaluate this equation on the tensor, and you get non-zero. So the rank is 5. I guessed them. No, sorry, but you mean in those?
No, the middle.
Those?
No, up one more.
Those?
Yes.
Those are obtained by flattening. So this is this contraction, this contracting. So when you act with E star tilde, Yeah, so the first one is by acting by E1 star. So a form that kills E2, kills E3, but has 1 on E1. So this is the only thing that preserves, and this tensor in matrix notation is this matrix. It has 1 as this coefficient and -1 and this coefficient on E2, E1. Yeah? So this is like E1 corresponds to the first row and E2 to the, to the first row and E2 to the second column. Now the second row and the first column. Here I take the first row and the third column. Here I get the third row and the first column. That's just the translation of a 2 tensor into a matrix. Yes. Do I have 5 more minutes or yes? Okay, so I wanted to prove this proposition because I was still a student when I learned about it, I remember. And Buczyński was the person who told me this, and I told him that this is too simple to be of any use. I didn't believe that this is useful because it's just really a restatement. But now I believe that maybe it's the most useful restatement that I ever learned. So let me, in last 3 minutes, present you the proof of this proposition. So if your tensor has rank k, it means that it can be written as a sum of k rank 1 tensors. But now, if you contract it with anything, it's obviously in the span of those rank 1 matrices. Yeah? If you replace it by whatever number, this exactly gives you a linear combination of those matrices. Yeah? So this direction is completely trivial. Now the other direction, well, you can always write your tensor, now the sum is up to n, in a basis, ei times something. Sum bi tilde times ci tilde. Yes? You can always write any tensor decomposing it into basis vectors. Sorry, there is a sum here, of course, like some. Let's say some. Let's call it mi for mi in B tensor C. Yes? Now, I can obtain mi by contraction. So by assumption, each mi is a sum of some bi's with some coefficients. So sorry, let's call them j, with some coefficients lambda ij. Now the sum is over j equal 1 to k. This is by assumption. There exist bj's such that each contraction, so in particular contraction by ei star, has to be a linear combination of those bj's, where bj is just some bj tensor cj. Yes? That's by assumption. But now we just put this thing instead of mi. So we are getting that T is equal to the sum, still n vectors, ei tensor, and now we have a sum from j equal 1 to k of lambda ij bj. But now we look at this sum, and instead of grouping by ei, we group it by bj's. So our sum will be by j, from j equal 1 to k. And we just look, what is the vector next to each bj? Well, it's a sum from I equal 1 to n, ei with a coefficient lambda ij. And I just presented our tensor as a sum of k tensors. Each of them is a rank 1 thing, because this is simply a product of two things, and this is some vector. This finishes the proof. If you would like to, I have some open problems at the end for you, like 2, if you want. I already gave 2. So there is, for example, one further one. I told you that we know the equations of sigma of the second secant variety. I told you that we know it for Segre. We also know it for Veronese, and we know it for Segre Veronese. But for example, it's open whether the ideal for a Grassmannian of a secant variety of a Grassmannian, is it generated in degree 3?
Is it just conjecture? Yeah?
Yes, conjecture.
You.
I don't think it's me. Maybe it's me. I don't know. I mean, people believe it. People believe it. It should be true. Thank you.
Thank you very much.